Hi Year 12. Today we're moving on to 7b in our chapter, and it's going to be looking at velocity and acceleration, but looking at them as derivatives. So in order to look at them as derivatives, we need to have a look at what that actually means, and they were the notes that we looked at the start of the last lesson. So I'll just move back to those and we'll go through those again. So we looked at displacement, and that was how far something was away from where it originally started. And then we looked at velocity. Velocity is represented by the letter V, and velocity is the first derivative of our x, or our displacement. So to find V, we need to work out what dx dt is, remembering that x itself is displacement, and that was up here. Let's highlight that as well. And these are your notes from last lesson. So the first derivative of displacement with respect to time is velocity, and it can be positive and it can be negative. Acceleration we looked at as well, and acceleration was a, and it was the first derivative with respect to time of velocity, or the second derivative with respect to time of displacement, and we can write that in terms of x with a double dot over the top. These are the rules that we'll be using while we're looking at velocity and acceleration as derivatives. We'll be relating them back to either displacement or velocity. If it's acceleration and velocity, we'll relate back to straightforward to displacement. So let's have a look at this first question. In example 1 says, the displacement of a particle is given by x is equal to minus t squared plus 3t plus 4 centimeters, where t is in seconds. So in this case, we're looking at centimeters and seconds, so our unit of measurements will be centimeters per second. This is the displacement of the particle. That's our x. And we want to have a look at the initial velocity of the particle. So let's think about what that actually means. Now, initial is right at the start, and initial is when time is equal to 0. That's always going to be the context of our language of initial in this topic. And velocity was equal to the first derivative of displacement with respect to time. So in order to find our initial velocity, we need to find our velocity. So we have our x, so we need to find what v is. So v is going to be dx dt. And if you do have a look at that, we do have x and it is in terms of t. So we're right to straight off differentiate that. So differentiating that, we're going to be getting minus 2t plus 3. And we want to find our initial velocity. So we want to find velocity when time is equal to 0. So I'm just going to times my minus 2 by my 0. I'll put that into the equation. And I end up with v is equal to minus 2 times 0 plus 3, which gives us velocity is equal to 3, but we need our units. We're in centimeters and we're in seconds. So remember, we can write it like that, or we can write it with a minus 1, either way. So that's the initial velocity of our particle. Part B would like us to show that the particle has a constant acceleration. Now think about what that means usually. When we have something being a constant, that means there's no variable term involved with our solution. So let's work out what our acceleration is and see what we end up with, and see if it actually looks like that it is a constant acceleration. So what was acceleration for us? Acceleration is equal to the velocity differentiated with respect to time, which means we have a velocity, so we can differentiate that, but it's also equal to the second derivative of displacement. So we've differentiated displacement once, which gives us velocity. So in doing that again, we're going to get our acceleration. So I'm going to differentiate our function here, and we're going to end up with minus 2. So acceleration is minus 2 centimeters per second, or centimeters per second squared. And we are saying that that is constant. There is no variable term after it. It's just a constant number. So our acceleration is constant in this case. Let's have a look at the next question. Part C says find when the particle is at the origin. Now, when the particle is at the origin, That's going to be when x is equal to 0. So in this topic, we're always assuming that we are starting at the origin, at time equals 0, and we're at x equals 0, unless we're told otherwise. So in this case, we haven't been told otherwise. So when is the particle at the origin? The origin's at x equals 0. We need time. So the when here tells us that what we're trying to find is time. What time is it at the origin? Well, let's look at our function back up here. I'm going to copy that down. So x is equal to minus t squared plus 3t plus 4. And because we're finding when x is equal to 0, I would like to let my minus t squared plus 3t plus 4 be equal to 0. And what you will notice there is we have a quadratic that if we solve, we're going to get values of t, most probably 2 values of t, possibly 1 value of t, and that's going to give us the when we are at the origin. So let's solve that. What I'm actually going to do is I'm going to divide through by minus 1 because I don't like that minus out the front of the t squared. So I'm going to end up with this equation. I would like that to add to minus 3 and multiply to minus 4. So what I end up with is a t in each bracket, and they're equal to 0. So I'll get t minus 4 and t plus 1. Minus 4 times 1 is minus 4, and minus 4 plus 1 is minus 3, which is what we want. So I will set each bracket to 0. So I get t minus 4 is 0, so t is equal to 4. And I'll get t plus 1 is 0, so t is equal to minus 1. And this is where we really need to look at what our answers are telling us. We have a positive time value and a negative time value. I don't need the negative time value because I can't work in the past. I only can work with time values after time is 0. So the value that I want is t is equal to 4, and I'm going to write a sentence answer. And that answer is the particle is at the origin at t equals 4 seconds. So in this case, we weren't at the origin at time equals 0. It took us 4 seconds to get there, so we started somewhere else. Find the particle's maximum displacement from the origin. Now this is where we need to really look at the language and think about what that maximum means here. So I'm going to highlight that and let you have a think about what did maximum mean to us before? How did we find things that were a maximum when we were using calculus? A maximum happened when we had a turning point, didn't we? The same is going to happen here. And we're looking at the turning point of the displacement. So what we want to find is we want to find where dx dt is equal to 0, and that should give us a turning point. The interesting thing to note here is when we're finding a maximum displacement, or when dx dt is equal to 0, dx dt is also velocity. So that is also when our velocity is equal to 0. And so generally when a particle is moving, it moves, and when it turns, its velocity for a little instantaneous point in time is 0 as it turns around. So this is correct. That's what we want to find. So we had already differentiated, but let's just look at that again. So x is minus t squared plus 3t plus 4. So dx dt we worked out before was minus 2t plus 3. And we wanted to find the time when that was equal to 0. So we're going to get minus 2t is equal to minus 3. So t is equal to 3 over 2. Or, if you like, 1.5 seconds. But that is only the time when our maximum displacement occurs. We want to find the displacement itself, which is our x value. So we're going to substitute that value here back into our x to get our displacement. So our x will become minus 3 over 2 squared plus 3 lots of 3 over 2 plus 4. So pop that in your calculator. And this will give us 6.25. Our units were centimetres. I've popped metres down there, but we actually want to have centimetres, so I'll fix that one up for us. 6.25 centimetres, and let's write that as a sentence. Find the particle's maximum displacement from the origin. My answer is that the particle's maximum displacement from the origin is 6.25 centimetres, and it's at 1.5 seconds. Okay, part E. We want to sketch the graph showing the particle's motion. Well, what we need to do on these diagrams for this section of our topic for motion is we want to have our motion to be shown as our x versus our time. So we need to have a vertical axis being x and a horizontal axis being time. So let's draw one of those in now. So you can see I've just popped an x and t diagram there. So we need to look at what's happening at all these points along here. Now I'm going to pop 0 down there. We're not looking at time is negative, so I don't want to have values down here. Sorry for my ums. Let's look at what we're going to pop in there. So what do we know? Let's look at what we've got and see what information we can put in there. So we're basically sketching this curve here. So what you can see from that x curve, it is negative. So we know that the shape it's going to take is something like that. We know when the turning point's going to be. We know that initially at time equals 0, we've got a velocity that is positive. So our dx dt is positive. So we know we're going to be going in that direction. We know that it has a constant acceleration. That's probably not going to help us. Part C is going to help us to start with. It says, when will the particle be at the origin? The particle will be at the origin, or when x is 0, at time t is equal to 4. So let's pop that in there. And we know that we're going to have a maximum displacement at time 1.5 seconds, and that's going to be 6.25. So I think we might pop a 6 and a 7 in there, and then we'll pop a little bit of that information in there. There's a 6, there's a 7. If we go 1, 2, 3, 4, 5, 6, 7, 8. Pop some values on your diagram as well. And I'm just going to start with this one up here. So we know that our maximum at 6.25 happens at 1.5 seconds. So 1.5 seconds is here. And that's our maximum turning point there that we've found out at 1.5 seconds. So we know at time equals 0. If I was to pop 0 in for my t, I get 4 centimetres. So right at the start, we didn't start at the origin. We started 4, 3, 2, 1, where we got 6, got a few little extra dots in there. We know that at time equals 0, I started at 4, and we're moving up here to reach my maximum value. Our other information we found was when also was the particle at the origin, and that was at a time equal 4. So if we go and look at that on our graph there, our particle is moving up, and it's going to come back down and be back at the origin at time is equal to 4 down here. We know that we had an initial positive velocity that goes in this direction. So we've kind of got the shape of our graph in there now. So let's have a look at the second question. The displacement of a particle is given by the formula x is equal to 1 plus sine 2t, where x is in meters and t is in seconds. Sketch the graph of x as a function of time, which is going to be pretty much the same as what we've done with y being where our x is and x being where our t is. So it's sine of 2x, and we're going to be moving up 1. So we're going to be oscillating, instead of between 1 and -1, we're going to have moved around a little bit. So let's get our axes drawn and see what we can do. And again, we're looking at time only being positive, so we're not looking to the left of our t, we're going to go to the right only. So think about what we did in our trig topic with drawing our graphs here and our translations. So normally sine oscillates around the x-axis. We've moved it up 1, so I've popped just a little dotted line to help us out here. So where we would normally oscillate around the horizontal axis, in this case it's time, we're going to oscillate around the line that's equal to 1 here. So the line x is equal to 1. And what's going to happen is we're still going to start at 1 instead of at 0, but our period is going to change. So where our sine curve normally has a period of 2 pi, we are dividing that 2 pi by 2. So we now have our sine curve having a period of pi instead. So we're actually squishing our curve up. So instead of it moving through 2 pi to get back to its original shape, we're going to be moving between pi, well, from 0 and pi instead. So it's going to squish our curve up more like that as opposed to. So I've just drawn it in there, so I'll talk you through it. So starting at 1, moving up to 2 where I normally would be at my point of 1, and finishing my curve back to this point here, which is equal to pi. So I've moved through one period of my curve to pi. Just pop some extra dots in there. That would then give us 2 curves in that 2 pi period. So that's the graph. So let's have a look at what the questions want us to look at. Find the times when the particle will be at rest. Okay, so let's look at the language of that. What does that mean? So when something is at rest, that would mean that it is not moving. If something is not moving, it has no velocity. So we're looking for a time when there is no velocity. Now, to find our velocity first, before we can find out when we have no velocity, we need to find our velocity. And that's our first derivative of displacement, or dx dt. Now, we now know how to differentiate trig functions. So we have our x up here. We are going to differentiate that, and we're going to end up with, thinking back to your trig functions, the derivative of sine is cos. It's going to be 2 cos 2t. And we want to find when this is equal to 0. So what we're finding is when 2 cos 2t is equal to 0, or when cos 2t is equal to 0. And when does that equal 0? Now there's a few ways that you can work out when cos is equal to 0. You can either think of the cosine curve itself. You could look at all stations to central, and then look at the first value in our brackets and look for when that is equal to 0. The other way a lot of people do is by trial and error on your calculator. I don't like the trial and error way. I'm going to look at all stations to central because I don't have a cos curve here with me. Or I'm not going to draw one. So let's think about our all stations to central, or what's happening in my unit circle. So if I had that unit circle, and I'm looking at my points that I would have at each of my axes, the x point is going to relate to cos, and the y point is going to relate to sine of theta or cos of theta. So let's pop some values on our all stations to central unit circle. So this little point here would be called 1 and 0. The point up here would be called 0 and 1. Over here would be minus 1 and 0. Down here would be 0 and minus 1. And we know that this line here is 0, 360. Up here is 90. Here's 180. And here's 270. So when we're wanting to find where cos of something is equal to 0, pop in your calculator. Yep, by all means. And that's the way I kind of call the trial and error. But I like to always practice at all stations to central. So we're looking for when that first value is equal to 0. That's going to be at 90 degrees and at 270 degrees. Now, that doesn't help us yet, does it? We need to look at this in terms of radians, because our axis here in terms of time is going to be in radians. So we'll fix that up in a minute. So I've said 2t then is equal to 90 and 270, and t therefore is going to be equal to 45 and half of 270, which is 135. We're going to need to pop some other values in there. We're going to need to go around that axis again, because we've halved our value here. We've had to halve our t value by dividing by 2. I then need to look at going around another time, or rather moving around my unit circle twice in this case. Oh, actually, I was actually wrong there. We're not moving around twice. We're moving infinitely many times around there because our particle hasn't given us an end time. So I've looked once around my circle and I've got 90 and 270. So if we were to go around again, I'm adding on another 180 basically to the numbers that I've got there up here. So I'm going to add on another 180 up here. So what have we got? We've got 90. Oops. Plus another 180. We've got 270. I'm going to go on another 180, which is 450. And we're going to keep adding on. So 450 divided by 2 is what? 225. And I want to now go and change these back to radians. So if you're happy to work in radians to start with, you can. But back to radians, when I'm going from degrees to radians, I'm going to times by pi over 180. So I'm going to have 45 times pi on 180, 135, and I'll simplify them down. Pi on 180, 225 pi on 180, which simplifies down to pi on 4, 3 pi on 4, and 5 pi on 4. Okay, let's look at the next question. Find the position of the particle at those times. We need to have a look at what our x value was. X is 1 plus sine of 2t. We need to pop those values that we've just found over here into our equation here to find what our corresponding values are. However, we've got the graph already drawn. Sorry, I'm just sliding down there. So let's have a look at the first one. When we're looking at time is equal to pi on 4, I can pop that into my curve and get a value on my graph. So when when time is equal to pi on 4, that pi on 4 would be just in here. So my graph is equal to 2 at that point. If you were to put that in your calculator and work out that, you would end up with the same value. But we'll say when time is pi on 4, x is equal to 2. When time is 3 pi on 4, let's have a look at what our x value is on the graph there. So 3 pi on 4 sits in here between pi on 2 and pi. And our value of x at 3 pi on 4 is equal to 0. Our next value that we're looking at is 5 pi on 4. So when time is 5 pi on 4, if you're not happy working in pi's, that was 225 degrees. That sits in here, and that'll get us a value of 2 again, which you can see up here. So what that tells us, if I keep going and pop my next value for time in there, I'm going to get a 0, and then I'm going to get a 2 in that case. So my particle is moving back and forwards between 0 and 2. Which I've just written here in a sentence. My particle is oscillating back and forth between x equals 0 and x is equal to 2.